Hello there, welcome to Chemistry Chapter 14, Final Exam Review. You'll need your worksheet and your calculator. And we'll begin here with number 1. So it says the instantaneous reaction rate of the following reaction is studied in a lab experiment. We have a reaction there. And then we have the data table with the concentrations and the reaction rate. And we want to know what is the rate equation for this reaction. Alright, so let's go ahead and write down the reactants. We have 2NO gas plus H2 gas, and we really don't need the products in this chapter, but I'll go ahead and write them down. N2O gas plus H2O gas. Okay, so we'll look at our data table. And we can see, if you just start with the first reactant, that it's held constant, NO is held constant between trials 2 and 3. So let's look at that first. So trial 2 to 3, the concentration of NO is held constant. Alright, so what happens to the second reactant, H2, between 2 and 3? Well, it goes from 3.5 to 7, so it doubles. Now, the reaction rate between 2 and 3 goes from 1.134 to 2.268. That is a doubling, so the reaction rate doubles. So when something doubles, that's like saying the concentration of 2, because the concentration doubled. Now, we're looking at H2, the second reactant. The exponent that goes with the second reactant is Y, and the reaction rate doubles, so that's also a 2. So 2 to the Y is equal to 2. Y then would be 1. 2 to the first power is equal to 2. Okay, let's take a look at the second reactant, H2. It's held constant between trials 1 and 2. So trial 1 to 2, the concentration of H2 is constant. Now the concentration of NO, the first reactant, between trials 1 and 2, if you look at your data table, it goes from 3 to 6, so it doubles. And that's always going to be the case, because that's the way the experiment is designed. And then the reaction rate between 1 and 2 goes from 0.2835 to 1.134. That's quadrupling, so by a factor of 4. If you're not sure, just take the big number and divide it by the small number, and you'll see that that equals 4. Okay, so that's like saying the concentration of 2. Now we're determining the exponent for the first reactant, that's x. 2 to the x equals 4. So x is going to be 2. So my intermediate, let's say, reaction rate equation before we find out K is R is equal to K times the concentration of NO to the second power, that's X, times the concentration of H2 to the first power, so that's Y. Now we want to fill in the data from one of the trials. I always choose trial 1, fill in the data, and solve for K. So in trial 1, the reaction rate is 0.2835. The unit is molars per second. Is equal to K. That's what we're trying to figure out. The concentration is 3 molar in trial 1. We have to square that. And it is 3.5 molar for H2. and that is to the first power. So K, we're going to bring these. So to do the algebra, divide both sides by these two. So we're going to bring them underneath. So 0.2835 divided by 3 molars squared times 3.5 molars. That's to the first power, which of course you don't have to write the 1. Okay, so let's put this in our calculator. So I've got 0.2835 divided by left parenthesis 3 squared times 3.5 right parenthesis. The whole denominator needs to be in parentheses there, or you'll get your order of operations off. So that's 0.009. Now I need to get the unit for K. So if you look at the unit, it's going to be molars per second divided by molar squared times molar. That's molars cubed. You would add the exponents. So that's the same as molars per second times 1 over molars cubed. That molar cancels. That goes to 2. And you get a unit of 1 over, and we usually put molars first, molars squared times seconds. So the unit is 1 over molars squared times second. Now this unit is going to be worth more than 1 point on the test. It's definitely a bigger part of the problem. So make sure that you're careful in determining the unit. So our final answer, the rate equation, R is equal to 0.009 1 over molar squared times second times the concentration of NO squared times the concentration of H2 to the first power, and we don't have to write the 1. Okay, so pause the video if you need to. I'll clear the board, and we'll do another one of these problems, which is number 2. So number 2 is a similar problem, whereas we have this reaction, NO3 plus O3. Do you remember what O3 is? Makes NO2 plus 2O2. O3 is ozone. All right, and we have a data table there. So we're going to go left to right. NO3 is held constant between trials 1 and 3. See that? So we're going to look at trial 1 and 3 first. So remember, those brackets just mean concentration. The concentration is held constant. So what happens to ozone? Well, if you look at the table between 1 and 3, it doubles. It's always going to do that. And then the reaction rate between 1 and 3 goes from 0.22 to 0.22, so it stays the same. Okay, so this is like, if it doubles, it's a 2 in brackets. The Y exponent goes with the second reactant, O3. And when something stays the same, it's like putting a 1 there. So 2 to the Y is equal to 1. Y then, anything to the 0 power is equal to 1. So Y is going to be 0. Now let's take a look at the second reactant, O3. It's held constant between trials 1 and 2. So from trial 1 to 2, ozone is constant. Concentration of NO3 doubles. Right, goes from 5.5 to 11, and the reaction rate between 1 and 2 goes from 0.22 to 0.88, so that quadruples. So that's like saying 2 to the x power, so if it doubles, it's 2. It's the first reactant, so it gets x. A lot of students get the x and y backwards. All right, so be careful. And quadruple is like a 4. So x is equal to 2. 2 squared is equal to 4. So our intermediate reaction rate equation without knowing what K is going to be K times the concentration of NO3 squared times the concentration of O3 to the 0 power. Well, anything to the 0 power is just 1. So that's going to be K times the concentration of NO3 squared. So that makes our equation pretty simple. So let's look at the data in trial 1 and fill it in and try to solve for K. So we've got a reaction rate of 0.22 is equal to the concentration of NO3 is 5.5 squared. And don't forget the K. So 0.22 is equal to K times 5.5 squared. So we're going to divide both sides by 5.5. So K is equal to 0.22 molars per second over 5.5 molars squared. So 0.22 divided by 5.5 squared. So that's 0.007, I'm going to say 0.0073. Now the unit is going to be molars per second divided by molars squared. That's the same as molars per second times 1 over molars squared. That molar will cancel. That 2 will cancel and go to a 1, so that's going to be 1 over molars times seconds. Okay, so we can get our final answer. R is equal to 0.0073, 1 over molars times seconds, times the concentration of NO3 squared. And then ozone is just not a part of the rate equation. The concentration of ozone just doesn't matter in this instance. Okay, I'll clear the board, and the rest of the problems are not going to take very long in comparison to these first two. So this chapter, most of the work is in these tabular problems. All right, number 3 says, what is the rate equation? We're given this reaction. The above reaction is second order with respect to NO, second order with respect to O2. What's the overall order? And then it asks for the instantaneous rate given these numbers. Okay, so we've really got 3 parts to number 3. So first we have 2 NO gas plus O2 gas. That yields 2 NO2 gas. So what is the rate equation if it's second order with respect to each of the 2 reactants? Well, it's going to be R is equal to K times the concentration of NO squared times the concentration of O2 squared, because the order tells you the exponent. The overall order is x plus y, 2 plus 2. So that is 4. Okay, and then we want to know what is the rate for the numbers given. So that's a K of 1.478, 1 over molars cubed, times second, times the concentration of 1.7 squared times the concentration of 0.78 squared. So we have 1.478 times 1.7 squared times 0.78 squared. That's going to be 2.598. Let's go ahead and just round that to 2.6. And the unit for reaction rate is molars per second. You could go ahead and cancel. So it's going to be molars to the fourth power here divided by molars third. That's going to just leave molars on top. Okay, number 4 says a chemist is bored to tears because the reaction he is performing in the lab is proceeding slowly. In order for him to get home by supper time, he must increase the reaction rate by a factor of 32. If the reaction is currently being run at 20 degrees C, at what temperature should he perform the experiment to get home before his beans get cold? All right, if he wants to increase it by a factor of 32. So what you need to think of this is 2 to what power equals 32? Well, x, if you haven't memorized these powers, x squared is 4, x cubed is 8, x to the 4th is 16, x to the 5th is 32. So each digit stands for 10 degrees. So 5th is 50 degrees. So if he wants to speed up the reaction, he needs to increase by 50 degrees. So that's going to be 20 degrees where he starts plus 50 degrees. So he's going to have to run the reaction at 70 degrees Celsius. All right, number 5 says, a non-chemist performs a reaction in a makeshift lab. The reaction moves too quickly, causing the non-chemist pain, anguish, and a melancholy countenance. In an attempt to give himself a happy face, the pseudo-alchemist decides to slow this reaction down by a factor of 8. If the reaction is currently being run at 15 degrees C, at what temperature should Alchemy Boy perform the experiment to achieve total bliss? All right, we need to slow down by a factor of 8. Well, 2 to what power is equal to 8? It is 3. So x is 3. That corresponds 10 degrees per digit. That corresponds to 30 degrees C. All right, so in order to slow it down, we must subtract 30 degrees C. So you'd have 15 degrees minus 30 degrees because the reaction is going to run slower as it gets colder. So that would be negative 15 degrees C. All right, number 6. A reaction performed at 25 degrees C has an instantaneous rate of 1.5 molars per second. If the concentrations are held the same and the temperature is raised to 65 degrees C, what will be the new reaction rate? And then it asks a second, what would the reaction rate be if the temperature were lowered to 5 degrees C? So 25 degrees C, if you raise the temperature to 65 degrees C, that is a difference of 40 degrees C. Okay? That means our exponent, x, is equal to 4. So we're kind of thinking backwards then from number 4 and 5. Remember, each 10 degrees stands for an exponent. So if you're going to be increasing, so we multiply. So our new rate, r, is going to be 1.5 molars per second times 2 to the 4th power. Okay, 2 to the 4th. This is the exponent. So 1.5 times 2 raised to the 4th power is 24. So our new reaction rate is going to be 24 molars per second. So that's part A. Part B, we're going from 25 down to 5 degrees C. So 25 degrees C, reducing that to 5 degrees C. That is a subtraction of 20 degrees C. So X is equal to 2. But we're not going to multiply because this slows the reaction down. So we divide by 2 to this exponent. So our reaction rate for part B is going to be 1.5 molars per second divided by 2 squared. So that's 1.5 divided by 4, which is 0.375 molars per second. So the answer to part B is 0.375. And finally, I can put number 7 right here. Says, which substance is a catalyst in the following reaction mechanism? So a catalyst, it'll be in the first reaction step, it'll appear as a reactant. And in the last reaction step, no matter how many there are, it will appear as a product. So that is nitrogen monoxide, or NO. That is your catalyst. And it asks, is it heterogeneous or homogeneous? All right, and because all the phases are gases, all the phases are the same, it is homogeneous or homogeneous, however you prefer to pronounce it. All right, that does it. This is an excellent review for the final exam. If you understand all of these problems, how to work them, you're going to be in good shape for the final exam. And I will talk to you on the next one.